Okay, so we're going to move on to lesson 4.7, which is making predictions using those best fitting lines that we were coming up with equations for in the last section. So the line that most closely follows the trend of data is called the best fitting line, or the line of best fit. And we can use this line and also the equation for that line to make some predictions. There's two types of predictions that we can make based on this information. So when we use a line or its equation to approximate a value between two known values, it's called linear interpolation. However, when we use the line or its equation to approximate a value that's outside the range of known values, that would be called linear extrapolation. So, for example, let's say I have a bunch of data for, the last decade or something, and I have the data from the year 2010 all the way up through 2015, and then I have a little gap, and then I have some more data from 2017 to 2020. Well, this year, right in here, if I want to make a prediction as to what was that value in 2016, even though we don't have the actual data, I can interpolate it because the line or the equation that I'm going to come up with is going to be based on stuff from before that year and also after. So it's something in the middle or in between known values that we have. That's interpolation. So if you think about the prefix in, inside, interior, it's in between data on both. So there's data both below it and above it. And this, what you're looking for or estimating, is something in between known values. On the other hand, extrapolation would mean that we're predicting something that's outside of our data. So let's say we have a bunch of data from 2010 through 2020, but we want to make a prediction about 2021 or maybe 2022 or maybe some other year in the future. So if we have a whole bunch of data prior to that year and we want to make a prediction as to what might happen in the future, that would be called extrapolation, because it's outside of the known set of data that we currently have. So if we interpolate using an equation, again, we need to find that independent variable and that dependent variable and set up our scatter plot the way we did in the last lesson. So again, my year here would be my X value. My pairs of nesting eagles here is going to be my Y value, because the year is the independent variable and the pairs of eagles would be my dependent variable. Now this table is showing the information. It's showing the number of pairs of nesting bald eagles from 1998 to 2002. We're going to make a scatter plot of the data. Then we're going to find an equation based off of our line of best fit that are going to model the numbers of pairs of nesting bald eagles as a function of the number of years since 1998. So 1998 is going to be considered year 0, which means 2000 would be considered year 2, 2001 would be 3, and 2002 would be 4. So notice we're missing 1999, sorry. And that would be year 1. Okay, so now let's plot these on our scatter plot. So 0, 5, so 0 is year 1998, so that's going to be on that x-axis or the y-axis. Then we have 2, 12. Then 3, 18. And then 4, 25. So now we want to write an equation that models the number of pairs of nesting bald eagles as a function of the number of years since 1998. So in order to do that, we do need to make a line of best fit here. Now, one strategy I like to use is if the y-intercept is a point that's kind of following the trend of the rest of the points, I do try to use that as one of my points. It kind of makes things a little bit easier for me as I go through. But then from there, how steep your line is going to be is going to slightly vary depending on how you draw your line of best fit. So I'm going to draw it like this. Okay, so you can see that I did go through the y-intercept, and then I also happened to go through this point right here. So those are the two that I'm going to use. So this one was 0, 5, and this point here is 3, 18. So I'm going to write my equation based off of those 2 points, but you could use any 2 points on your line of best fit, and yours could slightly vary from mine. So I'm going to use my slope formula, 18 minus 5 over 3 minus 0, and I'm going to get 13 over 3, which equals 4 1/3. So now when I go to write my equation in point slope form, this is why I like to use my intercept as one of my points whenever I can, because when I do y minus 5 equals 13 over 3 times x minus 0, it just makes it a little bit easier for me. So now I have 13 over 3x, and then I'm going to move my 5 over to the other side, making it a plus 5. Now, of course, when you're looking at actual data, 13 over 3 is a little bit confusing sometimes, especially if you have multiple different possible equations here. So if it's helpful, it might be helpful to write it as a mixed number or a decimal, especially if you're comparing different people's equations. So this shows me, okay, it's a little bit more than 4, my slope. Now, obviously, we know we need a positive slope here because this is a positive correlation, but someone else might have a slope of positive 5, or maybe just positive 4, or maybe some other fraction or decimal in that range or vicinity. Notice my y-intercept was 5 because that was one of my points, but if you didn't use those 2 points, you might have a y-intercept of 4 or 6 or some number very close to 5. So while there can be multiple answers based on how you drew your line, the slope shouldn't vary too much, and the y-intercept shouldn't vary too much. And if you look at the actual graph itself, like any y-intercept should be somewhere in that area, but look at your line and see where was your line crossing, and that should give you an idea. You definitely shouldn't probably have any negative answers for the y-intercept or anything greater than 10, because our line wouldn't really follow the trend of the points then, and we definitely should have a positive slope. Okay. And then the final question, C, approximate the number of nesting eagle pairs in 1999. So since I'm interpolating this data, it should be visible on the graph. So if I go to years since 1998, 1999 would be 1 year later. Now, if I follow this up to where my line was, you can see that it's right about there. So then if I go over to my y-axis, I can see that probably it was either 8 or 9. That would make sense. It's a little bit below the 10 on my line. Now, if you needed a more exact answer and you couldn't see it on your graph, maybe it was, in between and there was a big increment or interval used on your y-axis, then you could simply plug in for the x value. So if I plug in a 1, right, then I would have 4 1/3 plus 5, which would give me 9 1/3. Now, of course, you can't have 9 1/3 equal pairs, so you'd have to round that up or down to 9 or 10. So I'm going to say that probably 9 pairs is my best answer based on my line of best fit. So now we're going to now extrapolate some data using the same example. So using the same equation, we came up with an example 1. We're going to approximate the number of nesting bald eagles in 2003 and 2005. Now, you could potentially use your graph. So 2003, if this is 99, 2000, 2001, 2002, 2003 should be right around here. So you might be able to estimate that one using your graph, following it up. And I'm going to say it looks like maybe it's like 27 or something. But 2005 is way off our graph. So we're not going to be able to use the graph to make that prediction. So in that situation, just like I showed you here, we would just use our equation. So my equation is 4 1/3 times x plus 5. Now the year 2003 is going to be 5 years since 1998, so I'm going to put a 5 in there. Now 4 1/3 times 5 plus 5 is going to give me an answer of 26.66, I believe. So again, we can't have a decimal, so I'm going to estimate that it would be 27 pairs. And this would be for 2003. Now for 2005, this would be 2 more years later, so that would be a 7. So I'd have 4 1/3 times 7 plus 5. So if I put that on my calculator, I would end up with 35 1/3. So I'm going to round that to about 35 pairs. Okay, so keeping that in mind, and if you had a different equation, you may have 29 pairs or 40, or your numbers should be somewhat close to these, but they definitely can vary a little bit. So the actual number in 2003 was 31 pairs. We had estimated 27, so not too bad. And in 2005, there were actually 34 pairs, and we estimated 35 based on our equation. So as you can see, the numbers weren't too far off. And yours may slightly vary if you use different points than I did. So the accuracy, okay, so generally speaking, the farther out you go, the less accurate it will be. Now in this case, it just so happened that my 2005 was a little more accurate than my 2003, and that's probably just because of the slight variation in my line. But either way, they were both fairly close. Okay, so one more of these. Okay, so again, we have our years here. So we're going to use 1998 as year 0. So 2000 would be 2 years later, 2002 would be 4, 2003 would be 5 years later. So we're going to say years since 1998. Make sure we're labeling that. Years since 1998. So that means 1998 is the origin here. And then 1, 2, 3, 4, 5, 6, and so on. So this is 99, 2000, 01, 02, 03, 04, and so on. Now the y-axis here is going to represent the dollar amount spent. On these pet supplies. And you see our range is going from 21 to 37. So it's going from 21 to 37. I need to make sure I can fit all those numbers on my y-axis, but clearly I cannot go by ones because I will run out of space before I even got to 21. So we want to pick an increment that will make sure that we can fit all of those on our y-axis, but they're still spaced out a decent amount. So in this situation, 5 would probably be your best increment to go. So then we're going to start with 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. You could have probably also gone by 4s, but typically people go by either 2s, 5s, 10s, like easy numbers. So now we're going to plot our points and make our scatter plot. So in year 0, we had 21,000. So right there. Then in year 2000, which is 2 years later, we had 25. So 2 years later, 25,000. And then 4 years later was 32,000. And 5 years later was 37,000. Okay, so we can see that positive correlation emerging here. Predict the sales of pet care items for the years 2001 and 2004. So the year 2001, we need to make a prediction there. And then the year 2004, we're going to make a prediction there. Okay, so first I'm going to draw my line of best fit. Okay, not the straightest line, but you get the idea. So this one here is 2001. So I'm going to estimate that in 2001, it was about 30,000. And then over here, in 2004, I'm going to estimate that was probably about a little bit less than 40, so I'm going to say 38,000. Okay, now, of course, this yellow one here, the one in 2001, that was interpolation because I had both data points that I knew on both sides of that one. So I had stuff before and after it. However, 2004 would be extrapolation because all of the data that I had was before that prediction that I was being made. So in this case, the more accurate one would definitely be interpolation. We would expect that it would follow the continuing trend of the rise in sales. But as we go out into the future, there's a lot of things we can't predict, right? So we don't know if things are going to happen to the economy or there'd be something that pops up kind of like, any type of external type of thing that might affect the business in the future. We can only say if the sales are continuing at the same rate. Whereas when we're looking back and we're trying to interpolate something and we have data before and after it, if there was no major changes, then that prediction should be a little bit more accurate. And that is how you interpolate and extrapolate using your line of best fit.